Hey guys, I'm back at you live and here with another tutorial. Today we're going to be doing, oh god, what the hell's going on? I'm using a graphics tablet and it's very sensitive. Okay, today we're going to be doing Newtonian physics and gravitation. I haven't got a limit on the videos anymore, so I can make them as long as I want. Hopefully I won't make it too long, but we'll see how it goes. Why does it keep doing that stupid thing? Okay, go. Why isn't it writing anything now? What? What the hell? There ain't no time to waste, but us too blind to see. But in the end, you know it's gonna be me. You can't deny. Just tell me why every little thing I do never seems enough for you. You don't wanna lose it again. I know it. Okay. Let's do this. Gravitation. As you guys can see, my handwriting is getting progressively worse. So sorry. Ooh. Okay. Oh my god, the thing's spazzing out. Okay, a few equations you need to know. Why does it keep doing that? Can you please stop doing that, you stupid GIMP? Here we go. F is equal to ma, F is equal to mg, P is equal to mv. Okay, this is force, these two are forces, and this is momentum. Two of the main types of formulas you'll need for the A2 course. Let's do a quick tutorial on forces. So forces are, like, for example, if you have a force acting like this, for example, and we'll call that force F, then it has component forces acting along horizontal and vertical directions, and you can find them out by just multiplying by sine theta or cos theta. So that's resolving forces. I'm sure you guys know all this stuff anyway, so kind of stupid of me repeating this stuff. Of course, so if you have a guy, every force has an equal and opposite reacting force. So if this guy has a weight, which you calculate by mg of 50 newtons, he's very light, there'll be a reactive force of 50 newtons acting in the opposite direction. That's why you remain stationary on the ground. Okay, so that's a quick review on forces. Let's quickly do a thing diagram. Thing diagram? What the hell sort of English are you speaking? Oops. There we go. If we have a... Why does it keep going to white? I don't understand. If we have a slope, okay, and we have a point mass... Oh god. Why won't it let me draw stupid... There we go. If we have a point mass of 5 kilograms, okay, and gravity is 10 newtons per kilogram, then he'll have a force acting downwards of 50 newtons. Am I right? And if the slope is at a certain degree of thing, let's say it's 20 degrees, then we know that this angle here is going to be 20 degrees as well, right? And therefore the forces acting into the slope is just cos of 20 multiplied by 50 newtons, right? And the force that's acting down the slope is sine of 20 multiplied by 50. And of course, because there's Newton's third law, we'll have an opposite force of minus cos 20 multiplied by 50 acting from the slope outwards. But that force won't have any impact on the way the object moves down the slope because it's not acting down the slope. Why are these stupid dots? Annoying graphics tablet. And the force, okay, let me quickly work out what sine 20, sine of 20 multiplied by 50 gives you 17 newtons. 17.1 Newton acting downwards. And let's say there's a frictional force of 10 newtons. Okay? Then the resultant force is simply 17.1 minus 10, which is 7.1 newtons down the slope, right? And if that's acting down the slope, if there's a resultant force, we can use F is equal to ma. 7.1 is equal to the mass, which is 5 kilograms, times by the acceleration. 7.1 divided by 5 is the object's acceleration down the slope. That's how you use F is equal to ma. That's just an example of how you'd use it. And you can work out other stuff from that once you get the acceleration. And that leads me into the next topic that we need to discuss, which is Szilard equations and how fun they are. Lol. It's funny because they're not that fun, but oh well, whatever. So let's quickly talk about the Szilard equations. Szilard equations, yeah. That's my theme tune for them. The Szilard equations, these are just equations for constant acceleration. Again, stupid gimp. These equations apply for objects that have a constant acceleration. Okay? That's the only assumption that they have. There are other assumptions like no air resistance, all that stupid stuff, but the main assumption is that there's a constant acceleration, and they are v is equal to u plus at, s is equal to v squared plus 2, not s, what the hell am I talking about? V squared plus 2as is equal to u squared. No, at least, oh man, I'm messing this up, am I not? V squared is equal to u squared plus 2as. Is that right? Yeah, that looks about right. S is equal to ut plus a half at squared. S is also equal to, oh man, S is also, oh god damn it. S is also equal to Vt minus a half At squared. And then there's another one. What is the other one? Come on guys, help me out here. It's coming to me. No, it's not coming to me. What's the other one? There's another one. I'll be back guys, 1 second. Yeah, of course, here we go. It's S, oh god damn. S is equal to a half u plus v multiplied by t. Those are the 5 Szilard equations that you guys need to. Is that right? Oh man, why is this so annoying? Wait, let me just refer. Make sure I don't want to be teaching you guys the wrong stuff. I haven't done this in a while, so it's kind of annoying in that sense that I don't know them off by heart. But no worries, we have a book at our hands. I got this cool book called Essential Principles of Physics, and it has like everything to do with physics. So if you guys are planning on checking this out, probably be a good thing. It's literally got everything that you need to know in here. I'm just looking for the Szilard equations at the moment. I can't find them for some annoying reason. Probably like the 3rd page of the book, because it just seems that you know that the equations. Let me find it. Stop. Okay, for the sake of making you people wait, I'm just gonna pause the video. Oh well, would you look at that? I was actually teaching you guys the right stuff. These are the 5 Szilard equations that you need to know. And you can use them to work out different things. So, for example, let's say you shot a bullet, okay? So, we have this cool guy. Let's call him Tom Cruise. It's funny because Tom Cruise is not cool, but whatever. He shoots a bullet. The bullet's traveling at, let's say, 300 meters per second, okay? It hits a wall, okay? And it moves a distance of, let's say, 0.2 3 meters, and then it stops. If I give you that, annoying stupid thing. Yeah, if I give you that information, can you work out the time taken for it to come to a halt? If let's say that the person is 20 meters away, and that the speed stays constant for that duration of it firing 20 meters, how would you work out the time taken for it to come to a halt? Well, first we need to work out the time taken for it to move to the wall, which is just 300 speed. I'm telling you guys, I'm gonna get so annoyed. Stupid thing reverts to white ever again. Okay, it's just 300 divided by 20. Speed over distance. At least distance. Oh, God, I'm such an idiot. 20 over 300. It's equal to 2 over 30, which is just equal to 1 over 15. Which I don't know the answer to, so let's use the good old calc bud. That's equal to 0.06. 0.06 recurring, so 0.67 seconds, okay, to travel that distance. So let's call this time 1. Okay, so let me quickly erase this. Good. Okay, so time 1 is 0.067. Okay, now we have some more information over here. The object has traveled 0.3 meters. Its initial speed was 300 meters per second. Its final speed was 0. We don't know the acceleration or the deceleration in this sense. We don't know the time taken for it to do that. So what are we going to do? We need to find the time, right? So we're going to use a Suvat equation that involves time. And what Suvat equation involves both S, U, V, and T? It's this one. S is equal to U plus V over 2 multiplied by T. Okay? And we know what U and V are. It's just 300 plus 0. So basically S is 0.3 is equal to 300 over 2, which is 150 times T, right? So therefore the time taken for it to come to a halt would be 0.3 over 150, which gives us 2 times 10 to the minus 3 seconds. This is time 2. And total time T, is just equal to T1 plus T2, which is 0.067 plus 0.002, which gives us 0.00069 seconds. And that's our answer. And that's how you use Suvat equations in that sense. Whoa, what the hell? No, I don't want to do that. So that's a quick introduction to Suvat equations. I think that's most of the basic Newtonian mechanics that I need to cover for now. So I'm gonna bring it to a halt there. We're gonna move into gravity very quickly, because let's be honest, who has time? What the hell? See, I don't like GIMP at all. I was using Paint in my old PC, and having moved to Linux, Paint doesn't work here because it's a Microsoft program. So I'm forced to use GIMP, and GIMP is just the worst. So I do apologize for all these inconveniences that are being caused. Okay, let's move into gravity now. So what is gravity? Gravity is a force. It's one of the weakest forces, I think. It takes place between two objects. So if we have an object M1 and we have another object M2, then there'll be a force of gravity between the two of them. Okay, that's going to draw them together, and it's an attractive force. So what is gravity? It's an attractive force. Okay, it's weak, and also it's negligible, or at least negligible, what did I say? Negligible, uh, negligible, unless it involves one massive object compared to the other. So in this case, M1 or M2, one of them has to be more massive than the other, like very, very massive. So let's assume that M1 is very much more massive than M2. Okay, that's our assumption. I really don't know why it does that. I really don't know. Like whenever I press Control, for example, if I press Control and Z, it does that fine. Don't know why. If I double press it, why does it change color? I really don't understand. So okay. So force of gravity is attractive, all that stuff. Okay. It occurs for point masses. And that's an assumption that we're making. Because most of the time we're dealing not with point masses but objects, and we can actually do a special thing called a Gaussian transform, which we'll do later. Gauss's law we'll do later. But yeah, it's for point masses basically. And Newton had a law for objects that expressed this force of gravity. Why would you do that? You stupid program. I'm sorry, people. There we go. Point mass is, and Newton had a formula for that, which is F is equal to minus G m1 times m2 over the distance between them, r, squared. Let's say the distance between them is r. Okay, let's analyze this. Oh, look at this stupid ass program. Okay, so let's quickly analyze this formula. F is obviously the force between them. What is G? G is known as the gravitational constant. Okay, and it has a very small value. And one of the explanations as to why gravity is such a weak force is because of the fact that G has such a very small value. I don't know what it is, but it's extremely small, believe me. And yeah, as you guys can see from this equation, the force that's acting between two objects is something that follows a inverse square law. So the further apart the two objects are, the attraction between them will decrease by a square amount. So in other words, you can write that the F is proportional to 1 over r squared. It's inversely proportional to 1 over r squared. So yeah, this formula only applies for radial fields, which we'll come onto later on. Okay, let's leave this for now. Stupid GIMP won't stop being a pain. Don't worry, guys. I'll get another editor, or at least a paint-like program for my next video. So I'm gonna erase all this stuff, so as long as you guys made a note of it. Okay. So, oh, what the hell's this? What? Paint, GIMP, why do you have to be such a pain? Okay. So, let's say we have a field, at least Earth. Let's say Earth is a point mass, okay? All the gravity that, or gravitational force that it has, will act radially towards it, okay? Like it will act in from all directions, like this. And any mass that's in that field in that gravitational field will experience this force pulling towards it. Basically, that's what a gravitational field is. A gravitational field is a field whereby if you place a test mass, it will experience a force. That's basically what a gravitational field is. So yeah, so radial gravity works in the way that we use F is equal to minus. The reason why it's a minus sign, I forgot to explain, is because of the fact it's an attractive force. Because of the fact that it's attracting one object to another. And yeah, it'll become more apparent later on. So for large distances, where r is very much larger than the radius of the object of the Earth, let's say in this case a is equal to the radius of the Earth. When r, the distance between the two objects, is very much larger than the radius of the object, then you'll apply this formula, which is Newton's gravitational law. However, for let me quickly resolve this quickly. As we get closer and closer to the surface of the Earth, let's call this the surface of the Earth. Okay, these radial fields will actually act parallel to each other, and in this sense, we don't need to apply Newton's law of Newton's field law. We can just use F is equal to mg, which we already have been using for a long time now, because of the fact that at this close distance to the surface of the Earth, you can ignore the distance between them and the something else. The distance between them? What did I say? I'm such an idiot. You can just use gravity, the gravitational field strength of the object, instead of using the radial field. And the reason why we use this is because of the fact that it's not necessary to use the radial field, in the sense that it's a very close approximation to use just F is equal to mg. So what was I gonna do? Okay, let's do. I think we'll do gravitational potential energy now. Wait, let me just take a break. I'll just think about what we want to do next and get back to you guys really quickly. Okay, now that we've discussed what the two types of forces are that we are going to be applying, let's think about what G actually is. G is the field strength. We know that, and is measured in newtons per kilogram, right? But what's G defined as in terms of in terms of big G? Let's work that out. What the hell was that? That was annoying. Okay, let's redo that. There ain't no judge to ways, so just too blind to see. In the end, you know it's gonna be me. You can't deny. Maybe that's right. Every little thing I do. Okay. We know that the force that an object experiences close to the surface of the Earth is F is equal to mg, and it's also equal to g m1 m2 over r squared. Technically we don't need to use it, but it is equal to that. And because these forces are the same, we can equate them. So we get mg is equal to g m1 m2 over r squared, right? And because of the fact that we have m, oh by the way, this is technically m2, this is the mass of the object, and because m2 appears on both sides, we cancel them off. We end up with g is equal to g m1 over r squared. That's what g is equal to, the gravitational field strength. And it's not directional, it's a scalar quantity because of the fact that it's just a field strength, newtons per kilogram. And the way G varies, the gravitational field strength varies with r squared is evident from this equation. We can see that G is proportional to 1 over r squared, right? So in that sense, if we plot a graph, we'd see that my stupid thing worked. We'd see that G from the surface of the Earth, this is distance, and this is G. Okay, we'll call this RE, or the radius of the Earth. It would fall somewhat like this, not exponentially, but somewhat like that. Okay. What would happen here is actually somewhat like this, but you guys don't need to know why. Should I tell you guys about it? No, don't worry too much about that bit. It's due to some. Actually, I guess I could show you guys what would happen if it were a system of uniform density. I could show you what happened there, but it's difficult to explain the other bits. So if we look at the Earth, right? If we look at the Earth like this, and this is the center, right? The distance here is RE, the radius of the Earth. Once we get into the Earth, right? If it's let's look at that equation again. G is equal to Gm over r squared, right? Once we get into the inside the Earth, we, like, at any point we'll have mass that's beneath us and mass that's above us, right? So essentially we'll have a mass ratio, and if we assume constant density, we know that density is equal to, what is density equal to? Density is just equal to mass over volume, right? So the units of density in that sense would be, what would it be? It would be the mass, which is kilograms, or at least mass would be density times volume. It's equal to mass, right? And we know that the density of an object is, let's say it's rho, okay? And the volume is, if it's a spherical object, it would be 4/3 pi r cubed, right? Is equal to mass. And if we substitute this into the equation over here, we end up with G is equal to rho G 4/3 pi r cubed. And because these two cancel off, we end up with G being proportional to R, assuming constant or at least uniform density of the Earth. G is proportional to R in that sense, so G would vary somewhat like this until we hit the surface of the Earth, RE. It would vary in a straight line, but that's not the case because Earth has a higher density closer to the core. So that's that's my mom, sorry. So that's what we'd experience, but that's a bit too complicated. I'm gonna take a break. I have to go and eat something. My mom's calling, so I'll be back in a bit. And I'm back. Okay. What was I talking about? Oh yeah. So that's what will happen inside the Earth. But you guys don't need to worry about that. What was I gonna talk about? Okay. We've talked about gravity. Let's quickly review the actual equations that we have at the moment. We have the good old, what the hell? stupid ass game. Okay. Whoa, that was awesome. Okay. What am I doing? Oh yeah, I forgot to mention when I wrote down the equation, but did you guys notice how this equation doesn't actually care about M2? M2 is not included in it, so the field strength is independent of the object's mass. So that's very interesting. Whereas the force that the object will experience is varying, the actual field strength doesn't change. I thought, why? I thought that was pretty interesting. Okay, so that's what we have so far. I think we might also need to review a bit of a thing as well. Gravitational potential energy. Yeah. Okay. So if we have an object, let's say it's the Earth, and we have the Moon, distance between them, again we'll call it r. The energy required to gravitational potential energy, it's the energy required to move an object from infinitely close to the object to a set distance away, which in this case is r, and therefore gravitational potential energy is always negative. Okay, and we know that the energy that is required, at least we know that how do you say, work is equal to force times distance, right? So the energy, which in this case is GPE, is equal to the force that the object will experience at that distance multiplied by the distance, which is r, right? And what's the force? Because the distances are very large, then the force will have to be g m1 m2 r squared multiplied by r. And because the r's cancel, we end up with GPE being equal to minus g m over r. That's the formula for gravitational potential energy. But that's for large distances. Say we have an object that's 10 meters above the Earth's surface, very small distance. In that case, we'd have GPE is simply equal to minus mg h. The mass times the distance. Oops. What? It's basically force times distance again. Mg in this case is just the force at small distances. So I think that's about it for the formulas that you guys need to know. You have these two formulas for force. These formulas for gravitational potential energy. Right? And you have this formula that explains what G is. And from this you can work out the graph, etc., etc. Stuff like that. Okay. So that's good. Now we can move on to something else. Wait 1 second. There ain't no choice, babe, but to move on, and you know. Okay, let's clear up all this stuff because we don't need it. Essentially, that's the bulk of what we have to do with gravity. There's not much else we need to really know. Quickly talk about lines of equipotential, and I guess we could work out. Yeah, no, that's not the end. We need to talk about escape velocities and all that. So okay. So let's say, what was I gonna do? Gravitational potential. Oh yeah, lines of equipotential. Say this is the Earth again. Okay. Um, if it's a sphere, then it will have a specific distance from its surface where all objects placed at that particular point will experience the same force. If it's the same object, I mean. Um, and those are lines of equipotential. And the distance between these lines increases as they get further away from the object because of the inverse square law. So yeah, that's just another concept that you guys might want to know. I think to finish off, not much else we need to talk about, but to finish off, let's talk about whoa, what the hell was that? Yeah, okay. To finish off, I guess we'll talk a bit about let's see, orbiting fields and all that stuff. Again, we'll have the Earth and we'll have the Moon. Okay, and the Moon circles the Earth in a specific orbit, a circular orbit, not circular, but close to circular. And there is a force acting inwards, which is the force of gravity, and the Moon is moving outwards like that. And there's also a centripetal force that keeps the Moon in orbit, right? And the Moon's moving that way, forwards in that sense. Okay. Let's work this out actually. The Earth is pulling the Moon closer towards it, and so it has a force that's acting inwards, which is equal to minus g. Let's say the Moon's m2 and the Earth's m1. M1 m2 over r squared, right? But the Moon has a centripetal force that's acting the same way. It's how can I say? It's acting in the opposite direction, so it keeps it in the thing. And the way you work out the centripetal force is mv squared over r. And the reason why it's mv squared over r is because of circular velocity, and circular acceleration and stuff. Let me quickly equate this stuff. So here we have mv squared over r is equal to g m1 m2. By the way, this is m2 over r squared, right? Again, m2 cancels off, r cancels off, so we end up with v, or the velocity of the Moon, is equal to g m1 over r square root. That's what the velocity of the Moon is. That's the velocity it's traveling at that keeps it in orbit. If we want to work out the escape velocity, oh, by the way, let me quickly explain why this is as such. In circular motion, right, you have a concept called the angular velocity. Angular velocity is simply the number of degrees that an object moves in over the time taken. And there's also a relationship between angular velocity and linear velocity, in the sense that linear velocity is simply equal to the angular velocity w multiplied by r, right? So if we rearrange this for velocity, we'd simply have v is equal to theta over t. And now, most of the time to work out the velocity, you can just simply use the time period of one rotation. The time period of one rotation. That we'll call that t, okay? Big T. And you can also use the what the hell? You can also use the fact that because it's one full rotation, then the what? GIMP is a really difficult tool to use, I'm telling you people. You can also use the fact that for one complete rotation it would be 2, oh god damn, freaking GIMP. One full rotation is going to be 2 pi radians. Therefore, we can say that the velocity is equal to 2 pi r over t, right? So that's linear velocity based on circular motion. And there's also a relationship that a, acceleration, is equal to v squared over t. The reason why is because of the fact that we're differentiating it, but you don't need to worry too much about this. Not v squared over t, sorry, v squared over r. Oh my god, GIMP. V squared over r, and using f is equal to ma. We know that this is true because acceleration is equal to v squared over r, then f is equal to mv squared over r, right? So, simples. So that's working out the velocity of an object in orbit. If you want to work out the escape velocity, we have to use the other formula. Escape velocity is based on the gravitational potential energy. Gravitational potential energy we know as being GPE for radial objects is, obviously it's going to be minus gm 2 over r, right? And we know that the kinetic energy of the object in orbit is going to be mv squared, right? Half mv squared. And what we want to work out is this factor. What's the v that's required? What kinetic energy is required for the object to escape that orbit? And it needs to exceed the GPE, right? So we equate them. Half mv squared is equal to g m1 m2 over r. Again, this is m2 as well, so m2 on both sides, cancel that off. V is equal to, v squared is equal to, got 2 gm over r. V in this case is equal to square root of 2 gm over r. Notice the difference between the previous thing. It's basically double the square root, at least multiplied by a factor of, no, don't worry about that. This is the escape velocity. Escape velocity. This is the velocity required for the object to escape this particular object, in this case the Earth's gravitational pull. So I think that's about it on basic Newtonian and gravitational fields. Yeah, I think I'll come back to you guys with another tutorial, perhaps on astronomy maybe tomorrow. But yeah, I hope you guys like the new format, the longer format. I particularly like it because I get to talk a bit more, so you know. Anyway, I'll see you guys tomorrow hopefully, and hope you had a great Christmas, and yeah, I'll see you in the next video. Bye bye.